Hello, everyone. We're back and live with Hack Summit 2018, and we are thrilled here to be joined by Don Song and Raymond Cheng, who are the co-founders of Oasis Labs, and they're going to be telling us about their new scalable blockchain solution. And Dawn is a well-regarded UC Berkeley professor in the Electrical Engineering and Computer Science department, and she's won numerous awards, including a Sloan Fellowship, an NSF Career Award, an IBM Faculty Award, a Guggenheim Fellowship, a MacArthur Foundation Fellowship, and she was named one of the top 35 innovators in the world under the age of 35. And Raymond has similar accolades in his background. We're just so privileged to have both of them here. You know, Dawn just landed in Sweden just for Hack Summit to talk to us. She has a very busy schedule. She just launched her solution officially yesterday, and she's made time to talk to us today and to educate us. So thank you guys so much for being here today.
Thank you so much for having us.
Yeah, thanks.
It's our great pleasure and honor to be here.
Awesome. So we've got a huge engineering audience here that's eager to learn and thirsty to hear about what's new in what you're proposing here with your new blockchain. So I understand you guys have a presentation you'd like to give, but before we give the presentation, maybe I'd like each of you just to spend a minute talking about your background, how you got into programming, how you got into blockchain, your quick background story, so that we just get to know you as a person before we do the presentation. So Dawn, do you want to start with that?
Sure. Although you've already done a great intro. Yeah. Hi, everyone. I'm Don Song. I'm a professor at UC Berkeley in computer science. I've been a professor at Berkeley for more than 10 years, and I got my PhD there as well. My research has been in computer security, AI and deep learning, as well as blockchain. So I've been teaching blockchain and doing research in blockchain for a number of years now. And we see that there's a huge potential in blockchain, but also at the same time, we are still at a very early stage. There's so much to do. There's so much to build a more powerful infrastructure to enable the applications that we want to build. So that's why we are here to hope to bring blockchain technology to the next level.
Thank you, Don. And Ray, would you like to tell us a little bit more about your background?
Yeah, absolutely. So I did my PhD at University of Washington. I've been a researcher here at UC Berkeley for some time working with Don in the area of blockchain. I started back in decentralized systems when I was doing my bachelor's at MIT. I was working in the area of like distributed hash tables, early peer-to-peer systems. And so it's amazing to be part of this decentralized ride and working in the space for a while and see how far we've come. So my specialty is largely in the area of distributed systems and security, and been working with Don and Ditto on so much work to do. There's so much interesting research and new technology to build to get us to where we want to be.
Great, thank you, Ray. So Don, why don't you go ahead and start sharing your screen? And audience, while she does that, you can start to ask questions at the bottom of your screen. There's an Ask a Question button that you can click. So as you hear Don's and as you think of interesting things to ask about, you can feel free to do that. And then we will also maybe ask you a few questions later on. So Don, take it away.
Great. Yeah, thanks, everyone. So today, Ray and I will talk about Oasis, privacy-preserving smart contracts at scale. So I'm the founder and CEO at Oasis Labs, and Ray is the founder and CTO. So first, we're really excited to introduce Oasis Labs. We actually just launched yesterday. Oasis Labs is building a privacy-first, high-performance cloud computing platform on blockchain. And we are honored and thrilled to have a lot of support from the community, and it's great to see so much excitement, including the various press coverage about our launch. And also, given that this is a developers conference, we are really excited to tell everyone that we are launching our private testnet and invite everyone to join our private testnet. So please go to our website, www.oasislabs.com, for more information about joining our private testnet. Okay, so what is Oasis? What are we building? So Oasis is a privacy-first cloud computing on blockchain. And in particular, we focus on three parts. So the Oasis platform offers security and privacy protection and high performance to support diverse cloud-scale applications from games to machine learning, and has unique programming frameworks to support machine learning and analytics. And we achieve all this with decentralized trust without relying on any central party. So first, let's look at the problems that we are trying to solve. So blockchain holds transformative promises. It offers openness and transparency, integrity without relying on a central party, and enable digitally enforced agreements. However, what has blockchain really brought us so far today? Blockchain has brought us payments, ICOs, and CryptoKitties. So the question is, can blockchain help solve bigger problems? So what are some bigger problems? As we all know, data is a new oil, and a lot of this data is very sensitive. And we see on the internet that users are losing control of their data. For example, in the Equifax example that we have heard about, as well as the Cambridge Analytica scandal, as well as the recent Gmail issue. So on one hand, users are losing control of their data. And on the other hand, we see another problem where valuable data is siloed and underutilized due to security and privacy concerns. So we have the valuable data. On one hand, we would like to use the data for gaining business intelligence, to gain insights in the data. But on the other hand, given the security and privacy sensitivity of the data, we are also people are also concerned with the privacy breaches, data exfiltration, and so on. And as a consequence, a lot of this valuable data is now being utilized. It's being siloed, and the value is people are not able to extract value out of the data. So at Oasis, we are developing a new solution to address these problems. So all the problems that I have mentioned essentially is due to the core issue that privacy is difficult to get right and difficult to enforce. So at Oasis, we provide a novel solution to address these issues by providing a core capability called privacy-preserving smart contracts. Privacy-preserving smart contracts runs on top of the Oasis blockchain platform. It provides a number of properties. First, it enables automatic enforcement of codified privacy requirements, and without relying on any central party. It is designed to scale to real-world applications, including machine learning, and it's designed to be easy to use for developers without requiring any security or privacy expertise. So now let's look at a concrete example how a privacy-preserving smart contract can actually help us solve real-world problems. So let's look at an example of credit score services. So Equifax is one of the top providers for credit scoring service. And Equifax is a central party which has collected financial data on over 800 million people. And all this data is stored centrally. So in the Equifax example, Equifax owns and controls the data, and users have no direct access actually to their own data. And Equifax is responsible for securing the credit data, and Equifax decides what credit rating to give, and only Equifax talent is used to build the credit scoring algorithms. So as the figure shows here, the workflow shows that in the Equifax example, users' data is being collected, and Equifax uses data to, for example, train credit score models and to produce the credit score model. So when a new user wants to get her credit score, she can query the Equifax service, which will then return the user's credit score. And hence, as I mentioned, so in this model, essentially, it has the issues that I just mentioned above. And in the recent Equifax data breach, attackers were able to steal sensitive information about over 140 million people. So the question is, can we have an alternative? Can we have a different solution? So here is an example where we can provide a decentralized credit scoring on blockchain using the core capability that we provide for privacy-preserving smart contracts. So again, privacy-preserving smart contract is a smart contract, but with a strong privacy protection. So in this case, a developer could specify a privacy-preserving smart contract, and inside the smart contract, it can contain code for training a credit score model, and then also contain codes for serving the trained model once the model is trained. And also the smart contract can specify terms of use. For example, if users contribute data to the smart contract, then users can get rewards. So the smart contract can specify what type of rewards users can get. So for example, it can also try to reward early users with higher rewards than later users. And also the smart contract will can specify that the users contributed data will only be used for training the credit score model inside the smart contract, will not be used for anything else. Then in this case, users can have their, for example, financial data stored in the Oasis platform, but in an encrypted form. And when user agrees with the terms of use of this smart contract, users' data can then be contributed to the smart contract. As the smart contract gets sufficient data, the smart contract can train the credit score model to train a differentially private credit score model, which we'll talk about a little bit later. And then as the model gets trained, so now, for example, when Alice wants to get her credit rating, she can then query the trained model, which will then return to Alice her credit rating. So in this case, as you can see, we can enable this credit score service completely in a decentralized manner without relying on any central party. And we can protect users' data's privacy by utilizing the capability of privacy-preserving smart contracts. And also users can be rewarded following the terms of use of the smart contract. In this approach, with the credit scoring on blockchain using privacy-preserving smart contracts, it offers a number of advantages. One, users get to maintain control of their data. Even after they contributed their data to the smart contract, users still maintain control of their own data. And they can be assured that their data will only be used for training the credit score model in the smart contract, will not be used for anything else. And the privacy-preserving smart contract, essentially the privacy protection of the Oasis blockchain platform, offers privacy protection of users' data. And users gain benefit from contributing data as specified in the smart contract. And we achieve all this without relying on any central party. So now I've talked about the concept of privacy-preserving smart contracts. And then now let's look at what techniques are needed and what technologies that we provide to enable privacy-preserving smart contracts. In particular, how does the Oasis blockchain platform enforce privacy-preserving smart contracts? So privacy is actually a very complex concept. It has many different aspects. It's multifaceted. In particular, when we talk about privacy protection, there are at least two different aspects that we need to consider. One is that we need to protect the computation process from leaking sensitive information about the inputs. And 2, we need to protect the computation results itself from leaking sensitive information about the inputs, because the computation results itself is actually computed from sensitive input itself, and hence we need to be very careful that attackers cannot steal sensitive information about the input by just looking at the computation results. So in Oasis, essentially we provide two different solutions to address these two different aspects of privacy protection. So first, to protect computation process from leaking sensitive information, essentially we need to offer security protection at the computation layer. And in particular, in Oasis, we offer confidentiality-preserving smart contract execution to protect the computation process of the smart contract execution from leaking sensitive information. And to protect computation results from leaking sensitive information, we offer privacy protection capabilities at the application layer. In particular, we offer privacy-preserving analytics and machine learning to enable smart contracts to be able to perform analytics and machine learning while protecting user data's privacy. So now let's look at each one separately. So first, let's look at confidentiality-preserving smart contract execution. So again, the goal of this is to protect the computation process of the smart contract execution from leaking sensitive information about the inputs. So typically, when we do a smart contract execution, we provide the inputs, and the smart contract gets the latest state of the smart contract, and given the inputs, it will compute the output and also perform the state transition to achieve the new state. And then the new state will be committed to the blockchain. So with confidentiality-preserving smart contract execution, essentially in this case, so first of all, the inputs actually will be encrypted before it goes into the smart contract execution. And also, the entire smart contract execution happens in a secure execution environment, which essentially offers a practical way of computing over encrypted data. And in this case, also, the states that gets committed to the blockchain will also be encrypted. And the smart contract will do the state transition over these encrypted states. Even though the data and states are encrypted, still, our system is able to provide a proof of correctness to ensure that the smart contract has been correctly executed given the input. And we have a recent research paper describing this part of the technology in more detail. So the key to enable confidentiality-preserving smart contract execution is to utilize what's called secure computation. And again, the goal of secure computation is to protect the computation process from leaking information about sensitive data. And there are different types of solutions we can use to achieve secure computation. Mainly two different types of approaches. One is cryptography-based approach, including crypto techniques such as fully homomorphic encryption and multi-party computation, as well as a hardware-based approach. So one challenge for crypto-based secure computation is that the performance overheads can be very high. It often offers orders of magnitude performance overheads over native computation. We can also use hardware-based secure computation. For example, using secure hardware, which provides an abstraction called a trusted execution environment. It's also called a secure enclave. The advantage of a hardware-based solution is that it can offer very strong security and privacy protection, and at the same time, it's highly performant. Its performance is close to native computation. With trusted execution environments, we can run a program inside the trusted execution environment, also called a secure enclave. In this case, so for example, for the confidentiality-preserving smart contract execution, we can execute a smart contract inside the secure enclave. For the operating system and other processes that are run outside of the secure enclave, they will not be able to tamper with the execution of the contract and hence provide strong integrity. And also, they will not be able to learn the execution and the data of the program running inside the secure enclave and hence provides confidentiality. And also, the secure hardware also provides a hardware-based mechanism for remote attestation, which attests to remote verify about which program is running inside the secure enclave, as well as the initial state. By utilizing the remote attestation, one can obtain a proof of correctness that a smart contract has been executed correctly inside the secure enclave with the correct input and initial state. Secure enclave can offer as a cornerstone security primitive. It offers strong security capabilities. It can authenticate itself, the device. It can authenticate the software or program is run inside, and it can provide guarantees on integrity and privacy of the execution. Secure Enclave can serve as a platform for building new security applications that couldn't be built otherwise for the same practical performance. And there have been a number of examples earlier on building secure systems using Secure Enclave. And also there has been a growth in secure hardware development. All the different hardware manufacturers have recognized the importance of developing secure hardware. And hence over the years, they have all been developing various different solutions for secure hardware. However, we still have open challenges in secure hardware. In particular, how secure can it be under what threat models? And what would you entrust with the secure hardware? Would you entrust your Bitcoin keys, your financial data, or your health data? And can we create truly trustworthy secure enclave that can serve as a cornerstone security primitive that is widely deployed and enable secure systems to be built on top? If we can do this, we can really usher into a completely new secure computation era. So what's the path to trustworthy secure enclave? There are several important steps. First, we need to offer open source design. An open source secure enclave design can provide the transparency and that's needed for the whole community to analyze and verify the correctness of the secure enclave, and hence to enable the needed high assurance and trustworthiness. And also, an open source secure enclave design can help build a community for the open source project. And also, ideally, we would like to have formal verification of the open source secure enclave, and we need to ensure secure supply chain management for the manufacturing process. To address these issues, we have a research project called Keystone Enclave for open source secure enclave design. And you can find out more information at keystone-enclave.org. With Keystone, we are developing a full stack open source hardware enclave implementation for an open source RISC architecture called RISC-V. RISC-V is a high-quality, license-free, royalty-free RISC architecture originally designed from UC Berkeley. And this Keystone research project is in collaboration between UC Berkeley and MIT and with other university collaborators, and we are also getting a lot of interest from industry partners. For Keystone, we plan to have a first release this fall, with a more full-featured release coming next year. And RISC-V, as I mentioned, it's an open source RISC architecture, and the RISC-V Foundation has over 100 members. So RISC-V is widely adopted in industry. So that's the first part, how we enable confidentiality-preserving smart contract execution to protect the computation process from leaking sensitive information. So essentially, in this case, we execute the smart contract inside a secure execution environment with a combination of secure hardware as well as cryptographic techniques. Now let's look at the second aspect of privacy protection, which is to protect the computation results itself from leaking sensitive information. And this requires techniques at the application layer. So first, let's look at a concrete example why we should care about this problem. How can a computation result leak sensitive information about the inputs? Here, let me give you a concrete example of a recent work that we did in collaboration with researchers from Google. So in this research project, we explored a concrete question. We all heard about deep learning and neural networks. And training neural networks can help. So a lot of the recent advancements in AI and machine learning comes from neural networks, which trained over lots of data to perform different tasks, such as image classification, speech recognition, and so on. So one key question is, these neural networks have very high capacity. So do neural networks actually remember training data? And if this answer is yes, so can attackers actually exploit this phenomenon to try to extract the secrets in the training data from simply just querying the learned models? So here's an example that we did in our study. We looked at training a language model, which is used to predict the next letter or the next word in a sentence. And here, the learning task is to train a language model on an email dataset. In this case, we use the Enron email dataset. The Enron email dataset naturally contained actual users' credit card and social security numbers. From our experiments, by training, after training a language model on the Enron email dataset, we showed that an attacker can actually design new attacks that by simply just querying the trained models, the attacker is able to extract the credit cards and social security numbers that were embedded in the original email dataset. And this demonstrates an example that as we perform data analytics and machine learning over sensitive data, we need to be very careful protecting user data's privacy. And luckily, for this problem, we also actually have a good solution, which is to use differential privacy. So instead of just training a traditional neural network, a traditional deep learning model, here we train a differentially private neural network, a differentially private deep learning model instead. And we show that when we train a differentially private machine learning model, we can significantly reduce the memorization of the neural network, and also make it much harder for the attacker to extract the original secrets in the training data. So what is differential privacy? Differential privacy is a formal privacy notion. And the idea of the differential privacy is that here we consider two neighboring databases where they have just one data point that's different between the two neighboring databases. For example, here they have only one data point, Joe's data, that's different between these two databases. The goal is that now, when the analyst queries these two databases, the query results coming from these two databases should be almost identical, such that an attacker from just looking at the query results cannot really tell which database the query result is computed from. And hence, the attacker cannot tell whether Joe's data is in the database or not. So this is at a high level an explanation of differential privacy. And from this notion, you can see that differential privacy can help protect users' privacy, because an attacker cannot even tell whether the user is in the original database or not. So differential privacy is a very powerful notion of privacy. However, most of the previous work on differential privacy has either been theoretical, or the only practical deployment of differential privacy at a large scale is in very targeted, specialized application domain, such as the example application in Google and done by Google and Apple. And there's no previous real-world deployments of differential privacy for general-purpose analytics. There are a number of challenges for practical general-purpose differential privacy for data analytics. We need to provide usability for non-experts. We need to provide strong support for a broad spectrum of analytics queries. And we need to have easy integration with the existing data environments. No previous system addresses all these issues. In our collaboration with Uber, we have developed new solutions to address these practical deployment challenges by developing new techniques and solutions. And in particular, in our system, Chorus, we provide a framework for privacy-preserving analytics by enforcing differential privacy through query rewriting, where when an analyst submits a query, our system will automatically rewrite the query to embed the privacy enforcement system into the query to enable an intrinsically private query, which then can be executed on the original database, and then will automatically produce a differentially private results. And we also extending this work into machine learning to provide automatic differential privacy guarantees for machine learning pipelines as well. And this work has been deployed at Uber and also with open source release. And at Oasis, we are incorporating these advanced privacy-preserving analytics and machine learning capabilities into our smart contract framework, so that a smart contract developer does not need to be an expert of differential privacy or an expert of privacy to be able to leverage these capabilities to enable privacy-preserving data analytics and machine learning in their smart contracts. And this is a unique capability that the Oasis blockchain platform will provide. So far, I have talked about how the Oasis platform can help provide strong security and privacy guarantees for smart contracts. And so now I will hand over to Ray to talk about how we can achieve high performance for diverse cloud-scale applications from games to machine learning, and without relying on any
Great, thanks, hardware. Don. Let me see if we can do this slide transition without fail. So here, John spent a good amount of time talking about the formal security and privacy guarantees that the Oasis platform offers. And now I'm going to talk a little bit about some of the stuff that we're doing on the scalability side of things. And in particular, the goal here is to be able to provide high performance and a scalable computing architecture that'll support a diverse set of cloud applications, everything from games to machine learning on the blockchain. And so today, when people think about scalability, this is probably something that you guys have heard of before. Bitcoin gets 7 transactions a second, Ethereum gets a little bit more, and we want Visa level transaction performance, right? That's the claim that I'm sure all of you have heard previously. So if we go to the next slide, traditionally the way that we think about scaling blockchains is one of the main techniques is sharding, right? So obviously, if we think of a blockchain as a single lane highway, let's add more lanes and let's focus on high throughput transactions of these simple transactions. And tokens in particular are pretty simple in nature. Usually you think of them in terms of transfer logic, and the transfer logic of an ERC20 token is pretty simple in terms of computational complexity. Usually you're not touching a lot of data across different contracts, and usually they're quite simple in nature. Now, if we go to the next slide, smart contracts, actually, we envision a future where smart contracts are going to be much more complicated and touch a lot of data, actually. So some of the things that we want to be able to enable in our platform is to be able to support things like privacy-preserving machine learning. Perhaps a privacy-preserving machine learning contract can feed into a credit scoring contract that'll actually take data from a lot of different sources and compute a credit scoring model, which might feed into an insurance contract, which might feed into an escrow, which would interact with some form of tokens to actually handle the payments. Ultimately, we envision a world where we want to support smart contracts that have these very complex data dependencies and might be touching a lot of data that currently would not be possible in a decent fashion. So to give you a little bit of an intuition for some of the techniques behind our system, I'm going to try to give an analogy here in the context of a kitchen. Okay, so in a kitchen, let's say it's a burger joint, and the burger joint is trying to prepare, a bunch of hamburgers, and there might be a bunch of different sorts of burgers that you're trying to provide. So on the left-hand side, you have this refrigerator with vegetables and patties. And on the left-hand side, you also have this sink to dishwash and a chopping block. On the right-hand side, you have some fryers and assembly station. And the traditional way that we think about processing transactions is pretty sequential. So if I'm a cook, what I'm going to do is I'm going to grab some lettuce. I'm going to cut that lettuce. I'll put it on the plate. I'll grab a bun. I'll put it on the plate. I'll grab a patty. I'll fry the patty. I make sure I don't overcook it. Then I put it on the plate. And then, once I've assembled this burger, I'll, send it out to, my customer and send it to the dishwashing station. And if I have multiple chefs, one way that you could do this is to shard by hamburger, which is to say, if every single cook just does this in parallel, maybe we can get to something that is a little bit faster. The problem with this is that there are natural limitations to how much you can scale horizontally when you have this kind of when you do sharding in this fashion. So the problem here, if you've ever played this game, this will probably be laughably familiar to you, is that you're yelling at each other, you're trying to go through this this corridor, you're bumping into each other, you might be waiting in line to use the fryer. Ultimately, on-demand coordination can lead to a lot of contention, and contention is a real problem even in distributed systems as well. So if we go to the next slide, a much saner way to do this, and in a way that resembles how kitchens actually work, is that typically, you have somebody that's responsible for the cutting block, and somebody that's responsible for assembling, and somebody that's responsible for frying. And so in this way, they can actually act independently. So as the vegetable, if I'm there on the cutting block, I can cut the lettuce and toss it over to the fence to the assembler. Same thing with the fryer. I can fry. Somebody can be responsible for making sure that we don't overcook the burgers and send them over to the assembler. And the idea here is that it's not that we don't have coordination, but by coordinating ahead of time so that we have these specific functional roles, then these functional roles can act pretty independently. And they don't need to use this on-demand coordination quite as much, which would lead to constant collisions. They would have this mechanism to be able to optimistically execute. So as the person cutting tomatoes, I can cut some extra tomatoes because I know that the assembler is going to need it eventually. And we can optimistically execute and think of a different way to achieve higher throughput. So let me try to relate that now into the context of existing approaches in blockchains and how our scalable architecture is pretty unique and different in the way that we scale our system. So one of the observations that we've made in terms of how existing blockchains are built is that one of the common paradigms is that the computation of a set of a block of transactions, the storage mechanisms and the consensus are usually bundled together in one miner. And one of the problems with that is that consensus, just generally as a protocol, is typically pretty slow operation. It tends to be the bottleneck, and if you bundle them all together, you're going to be rate limited by the transaction throughput of your consensus protocol. The second observation that we made was that when you're sharding, so a typical way that one might scale the system is to do some form of sharding, and maybe we'll just have a bunch of these different subsets of workers operating in parallel. Maybe you'll do some form of state sharding, which is pretty a common idea in some of these other blockchains that we've seen. If you're doing sharding like this, coordination can become quite expensive due to contention, similar to the reasons that I was trying to describe in the analogy. So if you're using some form of two-phase locking system or atomic commit protocol, these tend to be very heavyweight sorts of protocols, and at the end of the day, they can lead to a lot of contention. In the worst case scenario, when you have malicious actors or malicious clients in the system, it's possible for these malicious clients to proactively try to introduce contention and lead to potential deadlock situations or live lock situations. So if we take a quick step back and think about what are the properties of a layer 1 blockchain that we would want. At the end of the day, there's a lot of different ways that people have tried to characterize what is layer 1. One way that you could try to define this would be using some terminology that we can borrow from the database world, which is to say that transactions should have ACID semantics, which is to say we have atomicity, consistency, isolation, and durability. Now, these are formal definitions, but informally, what this typically means is that for atomicity, every transaction either succeeds or fails completely. That is to say, if a transaction, if your worker fails or your miner fails halfway, you should revert back to a state where the state is consistent. You want to have some notion of consistency where the state transitions are only going to be between valid states. We want to have some notion of isolation. Isolation effectively means that the global state at any time is as if the transactions were executed sequentially. And it shouldn't be the case that there, even if you were to do any kind of parallelism or concurrency, the global state at any given time still reflects the situation as if it were executed sequentially. And some notion of durability, which is obvious. Obviously, we want some notion of persistence and fault tolerance, and the committed transaction should definitely remain even after some form of failure. So in our system, one of the main mechanisms and one of the main core techniques that we use is we actually try to separate execution from consensus. So we subsample a set of workers, which will act as a compute committee, a set of workers that will act as a consensus committee, and a set of workers that will act as a storage committee. And each of these committees have different responsibilities. So the compute committee will be responsible for processing the transactions in some kind of virtual machine environment. The storage committee is responsible for replicating and persisting state in a reliable way. The consensus committee will be responsible for reaching agreement on what is the current state at any given time. And so one of the goals of our system is to take a layered approach, one where we have an application layer. The application layer, the developers writing their smart contracts. In the computing layer will execute these transactions. The storage layer persists state, and we have a consensus layer that agrees on the state transitions and transaction ordering. And one of the interesting properties of our approach is that we can actually scale out this layered architecture for each layer independently, depending on what the workload requirements are. So some of the properties that we would expect from the system in the next slide. So in the next slide, some of the things that we do as part of our architecture, we do have to do some form of committee election. So committees are elected using a random beacon process in the style of proof of stake. Each one of these committees can operate completely independently, and we have a set of network protocols that allow them to coordinate in a trustless way. Optimistic execution allows these committees to execute optimistically to maximize performance. And so let me walk through, the data pathway of how transactions are processed in our system. So in our system, by separating execution from consensus, we first have a set of users submit transactions to a compute committee. Now that compute committee, these workers are stateless. We don't require any notion of a consensus protocol to operate between the compute workers, but each one of these compute workers can optimistically execute the transactions. And at this point, if there's any kind of failures, they would have no effect on state because we haven't actually committed anything yet. So these compute workers will first optimistically process a set of transactions, and for each one of them, they'll have their own idea of what you would expect the state to be after that block has been processed. Now, in the second step, the compute committee will commit the blocks to the storage committee. So we'll use some form of proof of replication. We can, leverage techniques such as Filecoin or IPFS to actually do the durable storage. But again, there's not really a necessary requirement for a consensus protocol. The main thing that's important is that the blocks are persisted and replicated, and if they're written, they would just be overwritten. So the writes are idempotent in that sense. So again, if the compute committee were to fail at this point, or there was if we had to re-execute these transactions over again, we haven't committed anything yet. The compute committees are doing all of these actions optimistically and writing into the storage optimistically. Now, the third and final crucial step is that we actually need to commit this to the blockchain. So at this point, the compute committee will commit the block root hash to the consensus committee. And we use a variety of techniques in the area of verifiable computation to actually check that the result of that computation was correct. If it is correct, then we can actually commit the block hashes directly into the consensus layer. We can execute a consensus protocol to make sure that everybody agrees. And in this case, the consensus committee will be responsible for tracking the sequence of state transitions and ultimately being the authoritative source of what the global transaction ordering is. But one of the things that's really interesting, if we head to the next slide, at a high level, this is a proof of stake blockchain, but one of the crucial properties here is that the consensus mechanism and the consensus protocol, that committee is, for the most part, largely off the critical path for the majority of the bulk data. The transactions are going through the compute committee. They'll be computed, formed into blocks, persistent on the storage committee. We can optimize those much better than we could otherwise, because the compute and storage committees don't necessarily need to run a consensus protocol. And then it's not until the final stage where we're actually committing the block root hashes to the consensus protocol where we actually need to run the consensus protocol. So one of the advantages here is that the data pathway and the large bottlenecks in the system are completely off the critical path from consensus. And in addition to that, each one of these functions can be scaled completely independently. And crucially, the aggregate system from end to end actually still provides the same guarantees that we would expect from any other layer one smart contract platform. So at a high level, that is the way that we achieve high performance. And one of the things that we're really excited about is that our unique scaling architecture actually enables us today to be doing things like machine learning. So within our own internal testnet, we've been developing some set of dApps to really demonstrate the true capabilities and the power of being able to do scalability this way, but also security and privacy this way. So the app that I really want to highlight and show you guys is an app that we've been working on called Kara. Kara is a privacy-preserving tokenized data marketplace for medical data. It's some work that we've been doing in collaboration with our peers at Berkeley, ETH, and Stanford. And this is going to sound familiar to you at this point, but medical data, like a lot of other data sources, are locked in data silos. And doctors and hospitals really do want to collaborate, and they want to be incentivized to share data to be able to improve medical research, which would only be good for everybody. So Kara, as an application.
And Ray, let me just interrupt you for a second here, Ray. We only have a few minutes left in the hour here.
Sure.
So if you want to maybe briefly describe Kara, that would be helpful to the audience, I think.
Great. Yeah, happy to. So at a high level, if we head to the next slide, this basically summarizes the sets of things that we're trying to do in Kara. It's a privacy-preserving tokenized data market. It provides a fast and easy way for doctors to earn tokens by sharing data with each other, and the data can be stored privately and securely on the blockchain. And in addition to that, we can actually do all of the training of the models in this privacy-preserving machine learning smart contract. So, the data we can prove that the data will never be leaked outside of that smart contract. And we can actually incentivize patients to upload their data and researchers to receive trained models to be able to do further medical research in a way that's fully privacy preserving. If we're running low on time, we can skip ahead a little bit.
We probably are running a little bit low on time, but maybe if you want to take maybe like one or two audience questions before we ended here, just to make sure the audience has had a chance to, and then maybe you could tell them where they can go to learn more about Kara. Maybe if there's a resource for them that you could point them to for the future.
Yeah, absolutely.
Yeah, I think so. Maybe we can just Ray. Maybe I can just conclude here then. Right. So, So on Oasis blockchain platform, as the example that Ray mentioned, essentially we are building this privacy-preserving smart contracts, and also within the smart contract you can actually do, for example, machine learning, and which couldn't be done today on today's blockchain. And hence, we hope that in the future, on top of the Oasis blockchain platform, we can enable blockchain of intelligent smart contracts, which can also help us to democratize AI. And to summarize, Oasis provides is building a privacy-first, high-performance cloud computing on blockchain. And again, we are really excited to have just launched Oasis yesterday. And also, we wanted to remind everyone to join our private testnet. So the current example that Ray just mentioned actually is a collaboration with one of the dApp developer who is building on top of our private testnet. So the dApp developer is actually building the app on our private testnet, and we are inviting other dApp developers to apply to join our private testnet to build your awesome apps on our platform. Yeah, thanks everyone. And for more information,
great. Thank you, Don. Thank you, Ray. So, I'm sure the audience may have questions for you. Is there an email address that you might recommend in case they want to learn more or chat with you, or other resources that you'd point them to? That way they can continue the conversation with you offline after Hack Summit?
Ray can write it in the chat.
Great, that sounds great. So maybe Raymond, you can do that. Mm-hmm. So I really want to thank both of you for being here. I learned a lot. It's incredible innovation that you guys have created here. The audience reaction during your presentation was fantastic. A lot of people really had their brain on fire learning about all these new concepts. And I think you made a big impact to everyone in the audience here. So thank you so much. I'm sorry we won't have time for more questions because we're just out of time at the top of the hour here. But audience, please feel free to email your questions to the team so that they can address those offline. And thanks again for being here and making time for us. We know how busy you are traveling to Sweden and with launching your new product. And so we feel very lucky to have you here. And so thank you so much.
Thank you for having us.
We'll be right back, guys, with
thanks.
The founder of Encent. It's a brand new startup company launching out of stealth mode here at Hack Summit. It's an exclusive for us. You won't want to miss this. We'll be right back.